Okay, so it's 4 o'clock, so we start. So we now have the first seminar in the context of this year's teaching. And it's a great pleasure to welcome Thomas Hertog from the Leuven Gravity Institute, which is part of the University of Leuven. Well, Thomas has done many major contributions to gravity theory, and in particular to, alone and in collaboration with Stephen Hawking, to understanding how quantum ideas apply to the universe and to cosmology. And that will be, I think, the subject of today's seminar. So, Thomas. One more announcement. Since everything is recorded, if you have a question, please wait for the microphone.
Okay, thank you, Marc. It's a great pleasure to be here. So the subject of Marc's course this year is the Wheeler-DeWitt equation. And perhaps the grandest application of the Wheeler-DeWitt equation is to describe the universe as a whole. The Wheeler-DeWitt equation provides a basis for a quantum description of the universe, and that will be, and that is the field known as quantum cosmology. Quantum cosmology it's a special field of physics. It takes you to some of the very foundational questions of physics. And some of the most vexing questions in quantum cosmology, one way or another, involve thinking about the observer, the act of observation, our position as observers within the universe. And so that will be the subject of my seminar today. And I think there are two key aspects of the observer in a quantum universe which really drive at the heart of this subject. I will first introduce these in general terms, and then in the second part of my seminar I will discuss a particular solution of the Wheeler-DeWitt equation which sheds some light on these questions to do with the observer in the universe. Now, I should say, as Marc has already mentioned, much of what I'm going to talk about today is really loosely based on discussions I've had over many, many years with Stephen Hawking, whom I met as a student in the late 90s. And we've kept collaborating on quantum cosmology for many years. And so I thought it would be fun to let Stephen introduce the two key questions that I want to discuss in this seminar. Of course, by the time I met Stephen, he was unable to talk with his natural voice, but he had a computer voice, as you know, and that's what you're going to hear now. So I will let Stephen introduce the first question that I'll be concerned with.
The universe appears designed. Why is it the way it is?
So it's rather cryptic, as usual with Hawking, but I'll explain. This is the first key conundrum, really, to do with the observer in the universe. It's the observation, it's a constatation, the observation that our universe appears designed, appears in some way biophilic. And by that we mean that if you just look out into space, well, then these are these cosmic clouds photographed by the James Webb Telescope. In these clouds, we find the organic molecules that one day could be the building blocks of life. Of course, the universe wasn't born with these clouds. These clouds are the results of 13 billion years of cosmic evolution. That cosmic evolution is governed by the laws of physics. These laws of physics appear to have a whole list of properties that make the universe eventually fit for life. Those properties concern the particle forces, the nature of the particles, the ratio of the forces, the composition of the universe, and even the simple fact that we have 3 large spatial dimensions. Change any of these properties of the laws of physics, and quickly you find that life as we know it will no longer be possible. That's an observation. And the observation leads us to ask the question, well, what about the laws of nature? What about the laws of physics? How should we think of them? How should we, why should they be fit for life? And over the years, many answers, of course, have been given to Stephen's question. Is this a scientific question at all, to probe the nature of the laws of nature? Is it somehow mathematical necessity ingrained in a final theory, that biophilic aspect of our universe? Are there many universes? Is there something beyond science in the form of an anthropic principle, or something different? So this biophilic nature of the universe quickly leads you to think about the nature of the laws of nature. And of course, the traditional view among many of our colleagues, ever since Newton, has been to think of the laws of physics as essentially mathematical truths, unchanging, fixed, somewhat Platonic kind of truths. A little bit like a barcode underlying the workings of the universe. That's also how Einstein very strongly thought about the laws of physics. Einstein must have been one of the first ones to really crystallize the idea of an ultimate, a final theory, a universal law, from which, as you can read, the cosmos can be built by pure deduction. The answer that Newton and Einstein would have given to the design question was clearly mathematical necessity. Ultimately, it's a mathematical truth. But as you can see, Einstein is looking a little lost. And in fact, I think it's Einstein's own work that sort of signaled the beginning of the end of this Platonic view of the laws of physics. And I want to explain this very briefly. I'm sure Marc wrote down Einstein's famous equation of general relativity for you. That's a classical theory, which essentially involves a dialogue between space-time, the geometry of space-time on the left, and matter and energy on the right. Einstein's relativity theory, of course, works perfectly well. It gives a very precise description of gravity in our solar system and well beyond it. The dialogue really between mass and geometry is really that manifestation of that dialogue is really what we call gravity. So where's the problem? Where's the problem with Einstein's theory? Well, like in many cases, the problem came from Belgium. Here is Georges Lemaitre. And Georges Lemaitre, 20 years after Einstein's theory, decided to apply his theory to the entire universe. And he quickly discovered that if you put all the matter and energy on the right-hand side, smear it out, look at the left-hand side, look at the space-time geometry, he found that in fact the old static eternal universe that we were familiar with from Newton and Einstein does not quite exist in general relativity. The universe must either expand or contract. An expanding universe, of course, was quickly observed because the galaxies are indeed moving away from us. Now, a few years later, Lemaitre did the obvious thing. Sorry?
I was just asking what was the contribution of Alexander Friedman.
Alexander Friedman found the same solutions found very similar solutions, but didn't quite do what I was about to do now, namely giving a revised physical picture of the evolution of the universe. So it's really the transition between pure mathematics and revising the history of our physical universe. That's what I'm about to say. So what Lemaitre did here was turn the arrow around. Of course, you can run the equation backwards in time. And he found that at very early times, the universe must have been completely different. In fact, if you run the equation all the way backwards in time, you arrive at what we know as a singularity, a moment in time, not an explosion, a moment in time where the curvature of space-time diverges. So that was a problem for Einstein's program to deduce the cosmos from pure mathematical theory. And indeed, that problem was exposed in the margin, in a famous discussion between Lemaitre and Einstein in the margin of the 27 Solvay conference, where Einstein clearly expressed his opinion on what this was all about. The problem, of course, is that Einstein's equation, general relativity, has the very strange property that it predicts a Big Bang singularity, but at that singularity, the theory also breaks down. So it predicts, the theory sort of has a strange property that it predicts its own demise all the way at the beginning. Strictly speaking, you would have to conclude that the actual origin, the beginning, lies beyond science. And so the design question was sort of up in the air at that point. Now, this was not Lemaitre's take on his own work. Lemaitre wrote, Lemaitre's take on it was, look at the title of the little paper he wrote, The Beginning of the World from the Point of View of Quantum Theory. So Lemaitre's take was that, okay, in these earlier stages, it's not physics that's going to break down, it's Einstein's classical theory, which must be generalized, morphed into a quantum theory. Now, to be clear, Lemaitre never wrote down a single equation that would then be able to describe that quantum origin. This was, at the time, pure intuition. Even quantum theory without gravity had just been invented, so clearly physics wasn't ready to say much more about this. Of course, as you know, later observational evidence was given for an early universe which was completely different from what we know today in the form of the microwave background radiation, the remnant radiation of the Big Bang. We now know that radiation isn't exactly homogeneous. There are flickerings in the early universe, there are slight temperature variations, they're of the order of 10 to the minus 5 degrees, and those 10 to the minus 5 degree fluctuations are perhaps the most mind-boggling biophilic features of the laws of physics, because if these fluctuations in the early universe had been slightly smaller or slightly larger, once again, it would no longer have been fit for life. You would either create a universe, evolution would either lead to an empty universe, a homogeneous universe, or a universe full of black holes. We seem to be right in the golden spot in the middle. So that's a very clear and tangible and observed connection between the early state of the universe 13.8 billion years ago and the fact that we have complexity today. So that's the first aspect of the observer in a quantum universe. This is not just any universe. There's something special about it. That specialness is ingrained in the laws of physics, and so that observation hints that at a very fundamental level, there must be a connection between the fact that we are asking all these questions today, that we exist, on the one hand, and the workings of the universe at the level of the laws of physics on the other hand. Now I'm going to let Stephen introduce the second question, the second aspect of this observer's viewpoint in a quantum universe. So bear with me.
I have changed my mind. A brief history of time is written from the wrong perspective. We are not angels who view the universe from the outside.
So once again, a rather cryptic comment. A comment he made to me many years ago, 2007 or 2008. And once again, it's sort of obvious. We're within the universe, looking up and looking out. This is different from most problems in physics. Most problems, most systems in physics, we're trying to understand from an outside viewpoint. Experiments at CERN, even astronomical observations. And that sort of objective outside viewpoint, that sort of Archimedean viewpoint, is ingrained in the way we formulate physics. Ever since Newton, we make a clear distinction between boundary conditions, which are not part of the laws, and dynamical equations. And that works. In fact, it's much the idea that we can look at the world objectively is one of the great successes of the scientific revolution, after all. But when it comes to these deeper questions in cosmology, we reach the limit of this system. Certainly, when we try to understand how our position as observers fits in cosmology, we must face up to the fact that we're not looking from the outside onto the universe. And so physics isn't really developed to do that properly, to implement that properly, to get this observer's viewpoint in the equations. And Stephen refers here to a brief history of time, because in a brief history of time, one of the highlights there was, and I will come back to this, was a theory of the Big Bang, which he had devised together with Jim Hartle. But the way he looked at that theory, the way he interpreted that theory at the time, in a brief history of time, is from the traditional sort of God, what Stephen then called a godlike perspective. A perspective in which you start with the laws of nature, they sort of transcend the physical universe, the mathematical truths, and you try to deduce a physical universe, in his case, a theory of the Big Bang that creates a universe, space and time, and eventually observers. And he had run into a problem. His theory of a brief history of time clearly doesn't work. In fact, it produced an empty universe. And so he was sort of back to the drawing table by the time I met him. So the question he's asking here, can we let go? Can we let go of this Archimedean standpoint? Can we sort of turn cosmology inside out? And you might think, well, this is impossible. But in fact, it's not quite impossible, because it's sort of what quantum theory tells us to do. As you know, quantum theory has many strange features, but one of the features is that the act of observation is not just something which happens from an Archimedean viewpoint, it's always an interaction with the system, and the kind of questions that you ask, the kind of observations that you do, determine the sort of reality that crystallizes. In fact, it's precisely this, as you probably know, it's precisely this subjective element of quantum theory that Einstein did not like. Einstein wanted a theory of physics that works independently of whether or not systems were observed. Bohr went along, here on the left is Bohr, took the act of observation much more seriously, but still sort of tried to find a middle ground, and the act of observation in Bohr's Copenhagen interpretation was something that was done from the outside after all. That would still not be enough to do cosmology. Really what you would do, what you would need to do quantum cosmology is a wave function that includes not just Schrödinger's cat, but the lab, the observer, anything, everything. So you would want a wave function of the universe, a universal wave function that describes various possible histories, various possible worlds, various possible outcomes of measurements. And you don't want to do this just in quantum theory. You want eventually to do this in quantum theory in conjunction with gravity. That's the field of quantum gravity, quantum cosmology, and so forth. Major developments were made in the 60s by John Wheeler and DeWitt, who finally wrote down the quantized version of the Hamiltonian constraint in general relativity that surely Marc has told you about. And we see that we now have an equation which is very different from Einstein's equation. It's an equation for a wave function of geometries. So we've gone from separate, classical, distinct, independent spacetimes to a wave function that is a functional of spacetimes and therefore describes for necessarily a superposition of various different possible universes. So that's a major step forward, of course, from the early days of Lemaitre. Lemaitre did not have an equation, but just some intuition. We are now 30 years later. Wheeler had an equation, but he still didn't have a solution. It's important to realize how fuzzy reality becomes according to the Wheeler-DeWitt equation. Such a universal wave function reaches in the future, of course. It will describe a superposition of possible future trajectories, but it also reaches into the past. In fact, Wheeler himself devised a famous experiment. I'm not sure you've heard about this, but it's often called the delayed choice version or variant of the two-slit experiment, in quantum theory, in which you place the detectors on the right of the screen. You place the detectors not at the two slits where the photons or the electrons pass through, but you decide to place the detectors behind the screen, on which usually the interference pattern appears. And the distance between the two slits and the screen could be light years, enormous. And the trick, the crux of the delayed choice variant of the two-slit experiment is that you decide way after the photons or the electrons have passed the two slits, way later you decide whether to open or close the Venetian blind at the screen. If you close the blind, the detectors won't be able to detect through which slit the photons or the electrons came, and you produce an interference pattern. If you decide at the last minute to open the Venetian blinds, the detectors will monitor where the photon comes from. And you will find two bright stripes, not an interference pattern. And so there's something very strange about this. How do the electrons on the photons know whether or not, whether they should behave as a wave and produce an interference pattern, or behave as a particle when they go through the two slits and produce two bright stripes? Because the decision to measure is made much, much later. Nature gets it always right. If you open the blind, you get two stripes. If you close the blind, you get an interference pattern. answer. Nature knows this because the past is not a given past. The past is a wave function. The past exists as a wave function, and a wave function is not directly observable. It describes reality at some pre-existence stage. And what kind of past emerges from that wave function is retroactively determined by the choice of the question, of the observation that one does later at the screen or one does at the present time. So the past is generally fuzzy in quantum cosmology. And yes, of course, please.
You are more generally referring to non-locality, presumably, here, when you talk about the past and the future, right?
Not necessarily, no.
Because this is, basically in these sorts of experiments, this is what plays the role, right?
No, non-locality I would rather associate with quantum entanglement. This is not even entanglement. Non-locality in
It's just to prove that it was impossible for the particle to be either a wave or an actual particle, because you know that it could not decide before the event.
There's no information, maybe that's the question. There's no information traveling back in time. It's just that observations and questions at a later time only then fully realize the past, which is a wave function up to that point. It's some sort of holistic, non-Copenhagen description of what the act of observation does. Yeah. But there's no information traveling back in time. All these histories are part of the wave function, and how these histories manifest themselves, in a sense you could say that the past is only fully realized through the questions asked later. And of course, Wheeler being Wheeler, he took that sort of, well, at the time this was a thought experiment, clearly. By now this has been done, this has been verified. But Wheeler being Wheeler, he took that sort of delayed choice thinking and applied it to the universe as a whole, as a sort of a very foundational feature of quantum cosmology. And he made a very famous drawing of the U stands for the universe. And, well, the Big Bang is upright. And so Wheeler envisions the universe expanding. And then you have that I on the left top right, standing for the act of observation. Of course, that's not a human eye, right? A photon could make an observation as well. But the key point of this figure is this dotted line to indicate precisely what I just said, that the history of the universe, if we think truly quantum mechanically about the universe, is only a definite, tangible, concrete history through the countless and countless quantum acts of observation that are happening all the time through particle interactions and so forth. And that has interesting implications, of course, for thinking about the origin of the universe and the fact that out of the Big Bang emerged a special universe. Was this ingrained from the start? Or should we think about this problem somewhat retroactively? That's really the question that Wheeler raises. But once again, Wheeler had an equation, a very conceptually difficult but profound equation, but not quite a solution. So now in the second part of my talk, I want to revisit these issues, these two issues, the biophilic nature of the laws of physics, and then what is the impact really of describing our observation and our observation situation from the inside. I want to discuss these two issues more concretely in the context of a particular solution of the Wheeler-DeWitt equation, which was found 20 years later in '83 by, as I mentioned, Jim Hartle and Stephen Hawking. Now, their solution, as you can see, it's eventually the abstract. What does it say? They're talking about a wave function of the universe that obeys the Wheeler-DeWitt equation, and they will and in this paper they put forward a very specific proposal for a solution for the wave function of the universe, which is inspired by the way we construct ground states of usual quantum systems in physics. How do we construct ground states? We often do this by conceiving of a Euclidean path integral. So they write down this very esoteric object, a path integral, a wave function, which will be a functional of the tree geometry and the scalar and the matter fields on a given slice of the universe. So that describes this ensemble, and they envision that wave function being defined or being specified by a Euclidean path integral. You see e to the minus the Euclidean action over h bar. Now, in order to fully specify that state, that quantum state, that wave function, you're going to have to specify the class C over which you do the path integral. And their proposal is that they're going to integrate over all compact positive definite 4 geometries, which have the tree geometry on which they evaluate the wave function, this configuration, as their only boundary. That's their proposal. I will make it visual and geometric in a minute. So positive definite 4 geometries, this means essentially Euclidean 4 geometries, right? That's the strange thing, that's the bold thing, that's the bizarre thing. We are familiar with Lorentzian geometries from classical gravity. Their statement here is that, wait a minute, geometries without a time direction, purely spatial geometries, Euclidean geometries, they are useful to describe quantum properties of gravity. And so, very concretely, what does this do? Well, we have, if we go back in time, classically, as I discussed, we go back in time and the Big Bang, the beginning, the origin of the universe will be a singularity. In a way, this is saying that if we stick to this clear distinction between space and time all the way back to the origin, we run into a problem. And so the reasoning now is, the reasoning of Hartle and Hawking was, maybe quantum effects in the very early stages become so important that even the distinction between space and time becomes a little fuzzy. And the second part of their claim was that fuzzy state we can describe, we can model not by using Lorentzian geometries with their clear causal structure, but by Euclidean geometries, wherein essentially the difference between space and time has been washed out completely. That's how you should think about the role of these Euclidean geometries. And what happens if you buy that claim? If you buy that bold claim, what happens is something remarkable. If you then go back in time, the statement is that quantum mechanically, a quantum description will not run into a classical singularity because in the earliest stages, the notion of time and space becomes, the time direction turns essentially into a space direction. But that creates a new possibility. If you have just space dimensions, you can, as you can see, these space dimensions can combine and sort of cap off the past into like a two-sphere, essentially very similar to the South Pole of the Earth. And so that's the crux of their solution of the Wheeler-DeWitt equation, of their proposal. This Euclidean path integral obeys the Wheeler-DeWitt equation. You can't solve it. This geometry is a saddle point approximation to that Euclidean path integral. But it's quite clear that by by morphing time and space together, you create this new possibility to avoid a singularity, to cap off the past, and in fact, in doing so, eliminate all questions of what came before the Big Bang. It's just gone. It's excised from your geometry. Now, this may sound like a very wild proposal, and I mean, I wasn't around in the 80s, but it must have been perceived as a wild proposal, I'm sure. But it was rooted in developments in the 70s in quantum gravity. Developments that had to do with black holes. You know a classical black hole. We've seen a classical black hole. We've photographed a classical black hole. That's the Schwarzschild geometry. That's a classical geometry. That's a solution of Einstein's classical equations. But what if you turn time into space in the Schwarzschild geometry? What if you turn the usual black hole solution of Einstein's theory into a Euclidean solution with 4 space directions? You get a very different geometry. You get some sort of cigar-like geometry. And what is inside the black hole is once again excised. It's a little bit like what came before the Big Bang in the wave function of the universe there. And then the horizon becomes this point where the cigar closes. Now, if you insist on regularity, if you insist that your geometry is always smooth at the horizon, that determines the size of the circle at infinity of the geometry. I'm talking about a Euclidean black hole solution here. Now, if you do that, you find something remarkable. You find that the size of the time dimension, the size of the circle all the way upright, sets precisely the temperature of the black hole, captures the famous Hawking radiation of black holes. So that was evidence in the 70s that Euclidean geometries are able to capture some aspects of quantum gravity systems. That temperature is the one you see on Hawking's tombstone, and that temperature implied that black holes have huge entropy, an entropy, in fact, proportional to the surface, proportional to the surface of the horizon, proportional to the area. Those developments, in turn, suggested that, wait a minute, maybe a fully quantum description of a black hole doesn't quite involve the interior. And so I mentioned here the interior of the black hole is gone. It would be to the right. Sorry, to the left for you guys. So this is somewhat similar. The amount of information that you need to describe everything that goes on inside the black hole can be stored in bits, in qubits, on the surface of the horizon. So that suggested that there's a fully quantum description of black holes may in fact be holographic. It led to the famous statement that black holes are holograms. Now that statement is confusing because on the left, a classical black hole is simple. It's just a hole in space-time. On the right, that quantum black hole, specified by bits and qubits on the horizon surface, is extremely complex. So classical space-time on the left emerges here from something very complex, quantum mechanical, on the right. But back to cosmology. So this was the crux of the solution of the Wheeler-DeWitt equation. The past was sort of capped off. And a key question, of course, was, well, how exactly does this transition from quantum to classical happen at the level of the expanding universe? On the right, you have a classical expanding Friedmann-Lemaitre universe. On the left, you have a quantum nugget, a quantum origin. The key prediction of this particular solution of the Wheeler-DeWitt equation is that this transition from quantum to classical happens through a burst of what we know as inflation. a burst of accelerated, rapid, potential-driven expansion. If it's why you need the potential-dominated phase of inflation in order to round, it's a regularity condition again. If you do not have a phase of inflation, you cannot glue smoothly, you cannot find a complete saddle point, you cannot glue smoothly this classical universe onto a regular quantum saddle at the left. But as I mentioned, these wave functions of the universe are functions of geometries. So a full solution, a full wave function will describe not just one particular universe, it will describe an ensemble. So you should think of the wave function of the universe as some sort of superposition of different possible histories for the universe. Each comes with a certain amplitude, namely you square the wave function and you can read off the amplitude. A major problem, a major conundrum associated with this particular solution of the Wheeler-DeWitt equation in the 80s is that the most, by far, the dominant, the highest amplitude, the highest probability lies at these universes that only undergo a brief burst of inflation. So a quantum burst, a brief phase of accelerated expansion, and then either a recollapse or an evolution towards essentially an empty universe. In fact, that was the problem in the 80s. That was why I mentioned before, Stephen wasn't getting any observers out of his theory of creation, because the universes were all that his theory was selecting were lifeless, short-lived, and so forth. But then come Wheeler. If you remember, we are not outside that wave function. We're inside. The kind of questions that we ask of the wave function of the universe are necessarily conditioned on our local observational situation. So we're not asking these a priori questions, whether we want or not to. And so it's very interesting that if you ask a more refined question, a question which is not just about any history, but a history conditioned on certain local, on certain observed features of the universe, then this distribution, this probability distribution predicted by the wave function drastically changes and selects, in fact, histories, universes, which in our past then undergo a very strong, long burst of inflation. And these huge universes which are in fact much larger than what we than the horizon size today. So Hawking underwent an interesting transition throughout his career. The early Hawking had his wave function, but looked at it from the outside. Looked at it at what he called a sort of a bottom-up way. He looked at the wave function of the universe like you look at the wave function of any other physical system. The later Hawking realized that in fact we are probing the wave function of the universe from the inside. And so we necessarily are asking somewhat more subtle questions. And so here you see very clearly Wheeler's vision going on right in front of your eyes in the context of a very specific, particular solution of the Wheeler-DeWitt equation. The kind of questions you're asking determine the past history that emerges from this ensemble of possibilities. And so this retrospective element that Wheeler had in mind is rather concrete here.
Can you be more precise? What type of question do you ask now? Is it like assuming that we are here, what is the probability of this and that, or
yeah,
is this? assuming something.
Yeah. Yes, I would ask roughly, yes, exactly. I would ask from the wave function a question, what are the probabilities for certain observables which we want to measure, given certain local data. For instance, the local distribution of galaxies, or certain pixels of the microwave background sky. And then you would ask, well, you would ask for other observables. What is the scalar tilt, or what are the number of e-folds of inflation in the past of this particular local observation situation? Given, of course, also you're working with a specific Hartle-Hawking wave function. And the situation is the following. If you do not condition, if you condition only on a few data, of course nothing is going to change. You are essentially still pushed towards a low number of e-folds. If you condition on enough data, in certain models of inflation, and I will specify which ones, there's a flip. And a different, for the experts, it's a little bit the cosmological analog of the page transition for black holes. If you condition on a lot of data, suddenly a new saddle point, which a strong burst of inflation appears.
But you are not losing some predictability. If you put a lot of data, it's clear that you are constraining and constraining and constraining.
That's right. That's right. Sure. Yes. You're certainly not. Yeah, I'm not sure. Is that a question or a remark?
Well, I'm not sure either.
No.
But I would say that if you are constraining by giving some data, it's clear that you are predicting less in a sense, because you are giving more information.
So the key question is whether the saddle point that then emerges when you condition depends on the nature of the data and the quantity of the data. And the answer is twice no, in fact. And to understand that, we need to understand when the flip occurs. The flip occurs when the potential that is driving inflation, when the derivative of that potential becomes less than the value of that potential to the third power, somewhat at the bottom of these instantons. Now, this is the condition for what is known as eternal inflation. So the statement, what is going on here is that if you increase the number of data, then all of a sudden, at some point, so in models where you have a regime high up the potential of eternal inflation, at some point there will be a flip, and saddle points up in the regime of eternal inflation will become to dominate. Now, those saddle points are completely independent of what kind of data you condition on, and also if you condition on a little more data or less data, it won't change anything. It's because it's way high up the potential hill. But you're absolutely right that this is not an a priori prediction of the theory. And this is, I think, why you're also saying, is this now a question or not? It is the realistic situation. We're not probing the wave function from the outside. So should we, and so whether we want it or not, a quantum cosmological theory, we are not testing that theory in circumstances that are purely a priori. And the striking thing is that taking this into account does matter. Are there only other questions? Because this is sort of a key point of the seminar. Okay. So once we realized this, we had exactly the same attitude as Marc had now. Is this necessary? Isn't this over-constraining? Isn't this putting in the answer? It's kind of, but on the other hand, it also works. Clearly, conditioning on a lot of data puts you on a saddle point that correctly predicts certain other data. And so we try to look for solid ground of this framework. And the natural question that came up, thinking back about black holes, is, well, maybe there's a better way to think about the wave function of the universe. Maybe there's maybe there's and so maybe also these ideas about holography are also applicable or important in cosmology. So we began to ask the question, well, is the universe as a whole also a hologram? Can we think about the universe just like for black holes? Can we think about the universe also in a holographic way? Because indeed, holography, as you might have heard, is much more general than just the statement that the entropy of black holes is proportional to the area of the surface of their horizon. Holography in high-energy physics has been developed into a whole framework for studying quantum gravity, a so-called duality, in the sense that gravitational theories in the interior of spacetimes are thought to be dual to quantum field theories on certain surfaces. So there's the name holography derives from the fact that it is a duality between a quantum field theory and a gravitational theory in different dimensions. The gravity theory, the gravity description has one dimension extra compared to the quantum field theory, the dimensions in which a quantum field theory lives. But now, how do you go about finding a holographic theory of the universe, of an expanding universe? There is no obvious surface on which you could project this gravitational system, except one, the obvious one, in fact. If you think about a wave function of the universe, a wave function of the universe is evaluated on a spatial surface. It's a function of the tree geometry and the matter fields. And so the obvious surface on which to project is in fact the surface on which you evaluate the wave function of the universe. In this case, in the case of the slide, this will be a surface at, say, at the present time, all the way up to the right of the slide. And if you project...
You mean now, evaluate psi now?
For instance, now, yes, at some moment of time.
Okay.
Yeah. Yes, sorry, yes. And if you imagine projecting this whole cosmological evolution on the surface now, you get some sort of Escher-like situation. The present time would be the edge of this disk. The origin of the universe, the Big Bang, would be in the middle, in the center. And of course, because the universe expands so much, much of the volume is piled up near the edge of this disk. The statement of holography would be that the gravitational wave function, so the solution of the Wheeler-DeWitt equation that describes the gravitational system, is in fact dual or equivalent to a partition function of a quantum field theory that lives at the present time, so that lives in this picture on the surface, on the edge of this disk. So the data of the wave function in this case are corresponding to data, to sources, to data of the dual partition function of the quantum field theory system on the boundary. So the unusual thing here is, of course, that which dimension of the gravitational system have we lost by projecting it out and applying a holographic duality and thinking about a wave function in terms of a partition function of a quantum system on the boundary. We have lost the time dimension. From the center to the edge of the disk is the time evolution of the universe. You might say, well, this is strange, this is special, but even in the case of black holes, it would be somewhat like that, right? Because if you take a black hole, if you go inside a black hole, you know that space and time flip. The interior dimension of a black hole is in fact the time dimension in a holographic description of a black hole located on the surface of the horizon. That would once again be, in fact, the time dimension which you lose. And of course, it was the time dimension which was the problem in cosmology all along. It's absent, in fact, at the level of the Wheeler-DeWitt equation, and it's radically absent in a holographic dual description of the wave function of the universe, where the interior evolution would be truly an emergent quality of the universe. In fact, the time evolution going towards the interior of the universe here would very much be encoded from the boundary quantum field theory perspective as an RG flow. You take the RG flow further and further to the IR, that corresponds to going further and further back into the past. And of course, from the quantum field theory perspective, there's a limit. These quantum field theories, they live on three spheres, they're Euclidean field theories on three spheres, say. So if you take the RG flow and you go all the way to the IR, at some point, you simply run out of degrees of freedom. That running out of degrees of freedom would correspond, in fact, to the Big Bang, would correspond to that cap-off that was the characteristic feature of the solution of the Wheeler-DeWitt equation that Hawking and Hartle found. So, to me, these latest developments, the attempts to construct a dual description of the wave function of the universe, sort of solidify that early top-down thinking, the retrospective thinking that I talked about. Because in holography, it's very much the boundary data, so the data today on the edge of the disk, which determine the theory, and then you move in. To quote Maldacena once again at the Solvay conferences, in holography, what defines a theory are the boundary conditions, the fields living on the edge of the disk here. So he wonders, maybe in our world, what defines a theory are the questions we're asking. Well, that's what you do on the edge. You define your question. And so I think holography sort of ties in, puts this top-down thinking on more solid footing. Now, what this means, I think is unclear. I think there's a deep lesson here to think about the origin of the universe from a holographic dual perspective, and I will conclude with some speculations on this. It has to do with what I just said, that if you go back in time from a holographic perspective, all the way back in time, at some point, you run out of bits. It's the holographic theory, the dual theory, just doesn't reach further back into the past. What would this mean? What could this mean from the usual bulk gravitational perspective? Or what new light could this shed on this somewhat magical capping off of the past in that solution of the Wheeler-DeWitt equation? I think it is telling us that in the earliest stages of the universe, So here's some sort of pictorial abstract diagram of how I envision the very earliest stages of the universe. You have the forces of nature as we know them today. In the earliest stages of the universe, you have a series of phase transitions. Essentially, these forces lose their specificity, they merge. And we've always thought that we would sort of land on some sort of ultimate final foundation. But I think the holography is telling us something different. But quantum cosmology is telling us something different, I think. I think this sort of merging this, and ultimately the distinction between space and time would disappear in this wave function. I think it is telling us that in the earliest stage of the universe, even the laws of physics disappear. I think it is telling us that the Big Bang is not just the origin of time, but also the origin of the notions of laws of physics. If you look from that perspective, the same picture, which is a picture of unification of physics, you see something very different, or you see perhaps something very different from how we traditionally envision a final theory as some sort of mathematical theory transcending the universe. To me, you see something much more biological, much more like a tree of physical laws that sort of branched out in the earliest stages of the universe, something much more like what people are familiar with in biology. So the answer that Hawking and I came up with in the final stages of his life to the question that he asked is, well, perhaps in the earliest stages there's hidden a deeper layer of evolution, a layer of evolution which played out at the level of the physical laws. So to put this in perspective, we have on the left Darwin's first sketch of the tree of life. We have on the right Lemaitre's first sketches of the evolution of the universe. For a century, we've tried to understand these two very different levels of evolution on ontologically completely different footings. Biology was always about emergent laws. Physics, cosmology was always about fixed, fundamental, transcendental laws. Maybe this difference was a mistake. Maybe these are two very different stages of evolution. And so I think what might be happening in quantum cosmology, what might be hiding in these solutions, these very abstract universal wave functions that are solutions of the Wheeler-DeWitt equation and that have no time in there, what might be hiding is a more general, is a slight epistemic readjustment of what physics is about, a more general notion of law, a notion of law that is not just a dynamical law like the laws we know, but that is some sort of mixture, some sort of combination of boundary conditions, dynamics, and also, the questions, the observer's perspective. So that's, I think, what might be hiding in these latest ideas of holography applied to cosmology. So that's what I wanted to say. Thank you.